Good morning, students. In the last class, we discussed the electrostatic potential and electrostatic potential due to a dipole, right? So today we are going to discuss electrostatic potential energy of a system of charges, right? So here we are going to discuss the electrostatic potential energy due to the system of charges, right? So as we discussed in the potential due to the system of charges, right? So here we have number of charges Q1, Q2, Q3 and Q4. So if we find the potential at any point from these charges, right? So Q1, Q2, Q3 and Q4, it is at a distance at 1p or 2p or 3p and or 4p, right? So here we are going to find the electrostatic potential due to these charges. We call these charges as a system of charges, right? So for that we have the relation V is equals to 1 by 4 pi epsilon naught q1 pi r1p plus q2 pi r2p and so on. If we have the n number of charges, we have q1 by rnp, right? So this is about the potential. Now we are going to find the potential energy. So what is potential energy? So potential energy is the work done in bringing the charge from infinite in an external field, right? So that one is the potential energy. Potential energy or electrostatic potential energy. So how we define the electrostatic potential energy? That is work done in bringing the charge from infinite to a point in an external field. So when we bring a charge in an external field, so against the external field we are bringing the charge, so there is a work done. So that work done we call as the potential energy. So here we are going to discuss potential energy due to the system of charges. So system of charges, we have so many number of the charges, right? So for the first, here we have the two cases. So the first case is we are going to find the potential energy in the absence of external electric field, or simply we call this one as the field. We are going to discuss the first concept, that is the first case, in the absence of the external electric field, right? So now bringing a charge q1 from infinite to a point A here. So calling this one as point A, we are bringing the charge from infinite to this point, right? So the charge is q1, right? So here there is no any external field. That means we are not applying any external field here. So that means the work done in bringing the charge from infinite to the charge q1 is 0 because there is no external field. So from the definition of the potential energy, work is done when we are bringing the charge in an external field, right? So here we don't have any external field. Hence, if we bring the charge from infinity to the point A, then work done is equals to 0. That is for which case work done in bringing the charge q1 from infinity to point A, right? So calling that one as work done W1, that is equals to 0, right? So first we are bringing the charge q1 from infinity in the absence of the external field, hence the work done is 0. So ಇಲ್ಲಿ ವರ್ಕ್ ಡನ್ ಆಗಬೇಕು ಅಂದ್ರೆ ನಮಗೆ ಏನಿರಬೇಕು, ಎಕ್ಸ್ಟರ್ನಲ್ ಫೀಲ್ಡ್ ಇರಬೇಕು. ಸೊ ಹಿಯರ್ ವಿ ಡೋಂಟ್ ಹ್ಯಾವ್ ಎನಿ ಎಕ್ಸ್ಟರ್ನಲ್ ಫೀಲ್ಡ್, ಹೆನ್ಸ್ ದ ವರ್ಕ್ ಡನ್ is 0, right? So now consider one point anywhere in the space, right? So it is at a distance. Consider a point B. So that point B is at a distance r R12, right? So consider one point B at a distance R12 from the charge Q1, right? So again, we are calculating the potential at a point B due to the charge Q1, right? So find the potential, that is potential at a point B due to charge Q1, right? So this point B is at a distance, that is R12 distance. So again, by the definition, the potential V1, that is at the point B, we are calculating the potential, hence we call that one as V1, that is due to charge Q1, right? So V1 is equals to 1 divided by 4 pi epsilon naught Q1 divided by the distance is R12, right? So we are calculating the potential at the point B, that is due to the charge Q1, right? So next, bringing another charge from infinite to point B. So that charge will be taken as Q2, right? So we are bringing the charge Q2 from infinity to the point B. So already we have the charge here. So due to this charge, we having the electric field. So if we have a charge means from this charge we are getting the electric field, right? So now when we bring the charge from infinity to the Q2, then here work is done, right? So the work done on charge Q2 due to electric field produced by Q1, right? So ಇಲ್ಲಿ ನಮಗೆ charge Q1 ಇರೋದ್ರಿಂದ from this charge we are getting the electric field, right? So when we bring the charge Q2, so ಈ charge Q2 ನ infinity ಇಂದ ಇಲ್ಲಿಗೆ ತಗೊಂಡ್ಬರ್ತಾ ಇದೀವಿ at the point B. So infinity ಇಂದ charge ನ ತಗೊಂಡ್ಬರ್ತಾ ಇದೀವಿ against the electric field. So ಅವಾಗ ಏನಾಗುತ್ತೆ ನಮಗೆ work done ಆಗುತ್ತೆ, right? So that's I have written here. So work done on charge Q2 due to the electric field produced by Q1, right? So in the last class we write the potential formula, that is work done per unit charge, we call that one as potential, right? So the ratio of work done per unit charge, we call that one as the potential. So here work is done on the charge Q2 due to the potential produced by the charge Q1, right? So we are going to find the work done. We can write W is equals to V into Q, right? So here we are calculating the work done on the charge Q2, right? So due to the electric field which is produced by Q1, that means the potential due to Q1, right? So for that work done W2, right? So that is equals to, from that formula, V1 Q2. So V1 is the potential which is produced by the charge Q1 and we are bringing the charge Q2 from infinity to the point B, right? So here we know the value of V1. So substituting W2 is equals to V1 is 1 divided by 4 pi epsilon naught into Q1 by R12 into Q2, right? So W2 is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R1. So calling this one as second equation. This is first equation, right? So here we are, this is the work done for the system of two charges. If they ask only for the two charges, so the total work done or net work done W is equals to W1 plus W2, right? So here W1 is what? 0 and W2 is this value. So we get W is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R1, right? So 0 plus this value, we get this value only, right? So this work done is stored as potential energy, right? So again by the definition, so that one U is equals to W. So potential energy is denoted by U, that is equals to work done, right? So here we have the work done, U is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R1. So this is the potential energy due to the system of two charges. So one is charge Q1 and another one is charge Q2. So without applying the external field or in the absence of the external field, the work done on charge Q1 is 0 because we don't have any external field here, right? So when we bring the second charge from infinity to Q, that point, so here this Q2 experiences the work done. That means it experiences the electric field. That means the force, right? So hence work is done, right? So this is for the two charges, right? So if they ask for only the two charges, this will be the final relationship. So if for the system of multiple charges, that means more than two charges, again the same step we need to continue again from here, right? Now consider one more point C, right? So this C is at a distance R13 from charge Q1 and R23 from charge Q2, right? So this point is at a distance R13 from charge Q1 and R23 from charge Q2. Hence, this point experiences the potential. That means we are going to find the potential at point C due to the charge Q1 and due to the charge Q2, right? So for that, potential at a point C due to charge Q1 and Q2. That is due to, we are going to find the potential due to system of charges, that is Q1 and Q2. We know for the system of charges V3 is equals to V1 plus V2, right? So V1 is the potential due to charge Q1 and V2 is the potential due to charge Q2. Again by the formula 1 by 4 pi epsilon naught Q1 by R1 3 plus V2 potential 1 divided by 4 pi epsilon naught Q2 divided by R23, right? So in this we can take common 1 by 4 pi epsilon naught Q1 by R13 plus Q2 by R23, right? So this is the potential at a point C due to the two charges, one is Q1 and another one is Q2, right? So again we are bringing one charge from infinity to the point C, Q3, right? We are bringing the charge from infinity to the point C. So that one is the Q3. So it experiences the electric field. That means work is done against the electric field which is due to the Q2 and Q1, right? So now work done on charge Q3 due to system of charges due to electric field produced. So E symbol represents the electric field. E produced due to charges Q1 and Q2, right? So that work done is W3. So W3 is the work done on this charge due to the potential of charge 1 and 2. We taken that potential as V3, right? So V3 and the charge is Q3, right? So again V3 we have here 1 by 4 pi epsilon naught Q1 by R12 plus R13 plus Q2 by R23 into Q3, right? So now multiplying inside the value 1 divided by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. So this gives the work done. Again, the total work done due to the system of three charges, right? So W1 plus W2 plus W3, right? So here W is equals to 0, W1 is 0 as we discussed in the earlier, right? So 0 plus W2 here and W3 is plus 1 by 4 pi epsilon naught. So within the bracket Q1 Q3 by R13 plus Q2 Q3 by R23, right? So this gives the total work done due to the system of three charges, right? So this work done as stores as the potential energy. So U is equals to 1 by 4 pi epsilon naught. So in these two terms, you can take this term as common, right? So if you take common here, plus Q1 Q3 by R13 plus Q2 Q3 by R23. So this is the potential energy due to the system of charges. So while solving problems, we need this formula, very important, right? Just for understanding purpose, I drawn like this. Right? So this is the potential energy due to the system of charges. So in the absence of external field, we need to remember if we take first charge as Q2, so here the work done W2 is 0. So here I considered Q1 as the first charge, so hence here work done is 0, right? So as your wish, you can take any one as the first charge, right? So here Q3 if you taken as the first charge, then work done at the Q3 is 0, right? So very important. So this is only when in the absence of external field. So in the absence of the external field, the first charge work done is always equals to 0, right? So next. So this is the potential energy. So potential energy is denoted by U. That means the distance, that is product of the two charges Q1 and Q2 and the distance between them, right? So if you observe here Q1 Q2 divided by R12. So Q1 Q3 divided by R13. Q3 Q2 divided by R23, right? So the same concept will apply when if you find the potential energy in the external electric field. So most problems they ask when in the absence of the external field, right? So you need to remember this formula. So the second case, in the presence of external electric field. So in the presence of the external electric field, right? So consider an electric field, right? So this gives the electric field, uniform electric field, right? So consider at any point on the electric field, so I consider point A on the electric field, so at this point the potential is V, right? So at this point the potential is V. Now bring the charge from infinity to this point A, at this point A from infinity, right? So here we already have the electric field, so work is done because we are bringing the charge from infinity to this point with the external electric field. That means the work is done, right? So work done on charge Q in an electric field E is given by W is equals to Q into V. Again, this is by the relation W by Q is equals to V. Work done per unit charge is equals to the potential, right? So at this point we have the potential V and we bring the charge Q, right? So hence work is done is equals to Q into V. So the work done is stored as potential energy. U is equals to W, right? So potential energy is equals to Q into V. This is for the single charge, right? So this is for the single charge when we bring the charge from infinity to the point in an electric field, right? So now, if the electron, right? So electron is the that is basic unit of the charge, right? So if the electron is moving in an electric field or accelerating in an electric field with a potential difference of 1 volt, right? So this electron is moving in this electric field with the potential difference of 1 volt, right? So then what about the energy? This electron gains the energy. So how much energy it is gaining? So that one we taken as U is equals to, so charge of the electron is 1.6 into 10 to the power of minus 19 coulomb, and the potential difference is what? 1, right? So 1.6 into 10 to the power of minus 19 joule, right? So this one we call as 1 electron volt. As we studied this, electron volt is the unit of the energy in atoms and nucleus, right? So how we get this value is when an electron moves in an or accelerates in an electric field with a potential difference of 1 volt, then it gains the energy. So how much energy? This much of the energy, that is 1.6 into 10 to the power of minus 19 joules, right? So we call this value as 1 electron volt, right? So the electron, when it accelerates in an electric field, it gains the potential difference of 1 volt, it gains the energy of 1 electron volt. So that if we written in terms of joules, so that value is 1.6 into 10 to the power of minus 19 joules, right? So this is for the single charge. Next, here we are discussing the system of charges. Again, here we have the electric field E, right? So consider two potentials on the electric field at a distance, calling this one as potential V1 and potential V2 on this electric field at a distance R12, right? So at a distance R12 we have the two potentials. Now bringing the charge Q1 from infinity to the point here where the potential is V1, right? So that one is the Q1, right? So from this relation, work done on charge Q1, right? So that is equals to W1 is equals to the charge is Q1 and potential is V1, right? So Q1 V1, right? So in the absence of electric field, the work done on Q1 is 0 because there is no external field. But in this case, here we have the external field and also we have the potential, right? So again from the relation, W by Q is equals to V, right? By using this relation, we get the work done while bringing the charge from infinity to the point where we have the potential V1, right? So now bring another charge from infinity to the point where the potential is V2, right? So we are bringing one more charge, so that charge is Q2, right? So now if you observe here, this charge Q2 experiences the force or experiences the electric field. Here we have the two cases, right? So it experiences the electric field. One is due to the external electric field and another due to the electric field which is produced by the charge Q1, right? So this charge Q2 has work done against the two electric fields. So one is the electric field is external, as we applied the electric field, that one is E, and the another electric field is the electric field which is produced by the charge Q1, right? So hence work done on charge or bringing the charge from Q2 to the point where the potential is V2. Right. Work done on charge Q2, right? So work done on the charge Q2, that is equals to work done due to external field. So one is external field, what we are initially applied, so that field we call as E, right? So plus one more, it experience done on charge Q2 we taken as W2, right? So W2 is equals to work done due to the external field. So work done due to the external field here, that is what we taken, W is equals to Q into V, right? So that is V1, right? So Q1 V1, right? Next Q2 V2 plus field which is produced by the charge Q1, right? So that one is the potential which is produced by the charge Q1, right? So V1 into Q1, right? So by this we have the potential due to V2, right? So that one divided by 4 pi epsilon naught Q1 by R1 into Q2 plus V1 Q1, right? So this gives what? The work done. So initially without external field we have only this much, 1 by 4 pi epsilon naught Q1 Q2 divided by R1. We don't have this extra quantity, that is V1 Q1, right? So here by the external field we getting the one more term, that one is the V1 Q1, right? So if we bring one more charge, so again it will add, right? So 1 by 4 pi epsilon naught Q1 Q2 divided by, so this distance is R1, right? So this is for the in the presence of external field. So one more quantity here we are getting the potential V1 and due to the charge Q1, right? So this is about the potential energy due to the system of charges, right? So concept is same in both the cases, but one extra quantity is adding in the previous case in the absence of electric field, where the work done on charge Q1 is 0, but here we have the work done is Q1 into V1, right? So in potential energy we have the last concept, that is potential energy of a dipole. So very important. So several times they ask for 3 marks. So in chapter ನಮಗೆ 3 marks in the question ಬರೋದ್ರಿಂದ ತುಂಬಾ important. In the previous, the relation between electric field and potential important. So in potential energy for 3 marks, potential energy on a dipole. So very important. Right. Potential energy on a dipole, right? So again, dipole is what? So we have the electric field, that is external electric field, calling this one as E, right? So consider a dipole. So dipole means two equal and opposite charges separated by a small distance, right? So here we have minus Q, here we have plus Q. So similar as we discussed dipole in an electric field, right? So the dipole moment is in the direction from minus Q to plus Q, right? So this is the center of the dipole. So this dipole makes an angle theta with the electric field. So dipole moment makes an angle theta with the electric field, right? So again here say force acting due to the electric field on plus Q charge, and here force acting on minus Q charge, right? So calling this one as F plus Q, here F minus Q. So same net potential is, sorry, net force on the dipole is zero because equal and opposite forces are acting. So as the forces are acting at the two different points, so there will be a torque, right? So we know torque that is equals to P cross E, right? So where P is a dipole moment and E is a electric field, right? So when angle is theta, that is between the dipole moment and the electric field, right? So tau is equals to PE sin theta into n cap, where n cap is the unit vector in the direction of the electric field, right? So now, so this torque has to rotate. So torque is nothing but rotate. So for rotating that one, small amount of work is done, right? So work done on rotating the dipole in an electric field, right? So that one we given. So small work done. Initially we taken for the small work done. So ಸ್ವಲ್ಪ rotate ಆದ್ರೆ ಅದನ್ನ ಸ್ವಲ್ಪ work done ಆಗ್ತದೆ. That means small work is done when this torque tau into how much rotation in a small rotation. So ಸ್ವಲ್ಪ rotate ಮಾಡಿದ್ರೆ ಸ್ವಲ್ಪ work done ಆಗ್ತದೆ. Now we are going to find the total work done, right? So for total work done, we are going to integrate this one, right? So the total work done, W, that is equals to integration of dW, right? So W is equals to integration. So dW we have tau into d theta. So applying the limits here from theta naught to theta, right? So this one is the initial theta, that means 0 degree to some 360 degree. So whatever angle we are substituting, so this one we are taken in the general form, right? So now the total work done W is equals to theta naught to theta. We have the tau value, right? So that one is PE sin theta into d theta, right? So where P is constant and E is constant, we are integrating the sin theta, right? So keeping P and E outside, so theta naught to theta sin theta d theta, right? So if we differentiate sin theta, d by d theta into sin theta, we get what? Cos theta, right? So in the same wise, if we integrate the cos theta, we get sin theta, right? So in the similar wise, d by d theta into cos theta. So if we differentiate the cos theta, we get minus sin theta. So you know differentiation and integration are reversible process, right? So if we differentiate one value, if we again we get one value, so if we integrate that value, again we get the same value, right? So here sin theta differentiate ಮಾಡಿದ್ರೆ cos theta ಬರುತ್ತೆ. So cos theta ನ integrate ಮಾಡಿದ್ರೆ sin theta ಬರುತ್ತೆ. So similar case cos theta ನ differentiate ಮಾಡಿದ್ರೆ minus sin theta. So that means minus sin theta integrate ಮಾಡಿದ್ರೆ ನಮಗೆ ಏನು ಬರಬೇಕು? Cos theta. But here we have the sin theta, right? So sin theta is ಅಂದ್ರೆ ಈ minus integration ಆದ್ರೆ ಏನಾಗುತ್ತೆ ನಮಗೆ? Minus cos theta. That means if we integrate the sin theta, we are getting minus cos theta. That means minus PE cos theta. Now we are applying the limits. Theta naught, theta. So theta naught is the lower limit and theta is the upper limit, right? So W is equals to minus PE. First apply the upper limit, right? So cos theta minus cos theta naught, right? So now minus is outside, shift into within the brackets. So minus into plus minus and minus into minus plus, that becomes cos theta naught minus cos theta. So this gives the work done. So this work done is stored as a potential energy, that is from the definition, right? Because these are the conservative forces, hence work done is stored as potential energy, right? So U is equals to W, that means U is equals to PE cos theta naught minus cos theta, right? So this is the potential energy due to the dipole, right? So very important for in 2019 they asked this one, either either they ask the relation between electric field and electric potential, or they ask for the potential energy of a dipole. So very important. So these are the steps. You can neglect this step, right? So directly you can jump from here to here. Next, by applying the limits, so this gives the potential energy. So for the dipole, initially we taken this angle theta naught is perpendicular, right? So here the dipole is like this, right? So this angle theta is 90 degree. So initial cases we taken dipole in this form, minus q to plus q. So then this is the electric field E, right? So now, if you observe here, angle theta is equals to initial, theta naught is equals to 90 degree. So substitute here, theta naught is equals to 90 degree. So cos 90 is 0. Then u is equals to Pe minus cos theta. Right? So this gives what? The final expression of the potential energy on a dipole. Right? So again, study the cases when is maximum and when is minimum and when is 0, right? So this is also important, for either they ask for 2 marks or 1 marks, when is maximum and when is minimum, right? So when theta is equals to 0 degree, right? So starting point is here, this gives what? Theta naught. Now we are going to rotate this dipole. So either in clockwise direction or anti-clockwise direction, right? So initially this theta is 0 degree. So cos 0 is 1. Then we get the potential energy is minus Pe, which is minimum, because we are getting minus value, right? So when theta is equals to 180 degree, right? So that means we are completely rotating by 180 degree, right? So for that, cos 180 is minus 1, so potential energy U is equals to Pe. So here we are getting the maximum, right? So now rotating this by the angle 90 degree, that means exactly in the direction, dipole moment is in the direction of the electric field, right? So when theta is equals to 90 degree, right? So cos 90 is 0, then U is equals to 0, right? So minus 1 is, this gives what? Minus 1, which is less than 0, hence this value is minimum, right? So these are the special cases. So these are also important. If you know this relation, you can easily find when is maximum and when is minimum, right? So this is about the potential energy on a dipole, right? So this is about electrostatic potential. Here we discussed potential and potential energy. So there is a slight difference between the potential and potential energy, and also in the formula also, right? So very important topic. So in the next class we will continue by solving the problems on based on these two topics. So very important for 5 marks. So one problem will be come from these two topics, right? Then